This video tries to explore and explain some of the inadequacies of Newton's theory of gravitation and deals with things at around the high school level. Ultimately, it's in preparation for considering Einstein's theory of general relativity, the 20th century theory which replaced Newton's theory. And if you were to stick with this series of videos, you'd see exactly why this kind of equation from Einstein replaces this kind of thing from Newton. But one is bound to ask the question is, what exactly seems to be the problem with Newton's theory of the 17th century? It's served us well since that time, and the predictions it makes are known to be extremely accurate. However, there are some issues which have to be brushed to one side in applying those laws, and the theory was known even by Newton to be incomplete. This video, therefore, will spend a little time reviewing the ideas of Newton, his laws of motion and his laws of gravitation, in order to appreciate what those issues are. And all of this will be done by considering velocities which are much less than the speed of light. In other words, we shall ignore special relativity at this stage. This is basic Newtonian mechanics and gravitation, and we'll be thinking here about fairly weak gravitational fields and about objects moving at fairly slow velocities. The later videos in this series, if you were to stick with them, will start to consider how the problems with Newton's theory can be answered by Einstein's general theory of gravitation. But for now, let's explore some of the frustrating issues around Newton's theory. Before looking at the ideas of Newtonian gravitation, we should quickly remind ourselves about Newton's laws of motion, in particular his second law. In one version of it, this states that the rate of change of momentum of an object is directly proportional to the force applied and takes place in the direction of the force. If we use the symbols F for the force applied, m for the mass of the object, v for its velocity and t for time, we can then write Newton's second law, ignoring for now the details of its vector nature, as F is proportional to d by dt of mv, where mv, mass times velocity here, is the momentum. In later videos we'll tend to use the letter P for momentum mv, so this law would be written F is proportional to dp by dt. But that's a long way off, and so we'll stick with mv for now. And starting with this expression of proportionality, we then define our unit of force, the Newton, in a particular way, and we do it such that the constant of proportionality in this equation is equal to 1. In that way, we then have Newton's second law as F equals dmv by dt, where in SI units the mass is in kilograms, velocity is in meters per second, time is in seconds, and the force is in newtons. And given that in Newtonian mechanics we generally have situations where we can assume that the mass of the object remains constant, this equation becomes F equals m dv by dt, where dv by dt, the rate of change of velocity with time, is of course acceleration. And so most people think of the equation for Newton's second law as F equals ma, force equals mass times acceleration. In broader terms, this tells us that mass being constant, a force will produce a change in velocity, either in its size or in its direction, or both. Now I'm sure you realise that the mass m here has nothing at this stage to do with gravitation. It is what we might term the inertial mass of the object. It's the property of an object which appears to make it resistant to a change in its motion. And that word resistant, of course, is not a good descriptor to use here. Resistance, in the context of forces and motion, usually implies an opposing force and a subsequent dissipation of energy, as used in terms like air resistance or frictional resistance and the like. Inertial mass is definitely not that kind of resistance. It's simply that a high mass object requires a large force to change its momentum by a given amount in a given time, whereas a low mass object requires only a small force to change its motion by the same extent in the same time. And this idea of the mass of an object, the inertial mass of an object, is independent of gravity at this stage in our thinking. Imagine, for example, being in a spaceship in deep space, far away from the gravitational pull of other stars and planets. In that situation, with no gravity to worry about, we could say that everything in the spaceship is what we might call weightless. They're not just in orbit around the Earth, they are far, far away from anything. However, the occupants of the spaceship would still realise which objects around them had high mass and which had low mass. Granted, any untethered objects in the spaceship would simply float about, but the occupants would easily realise that high-mass objects would be difficult to get moving, and once moving would require a large force, or a small force for a longer time, to get them to slow down and stop, or to change their direction. Changing the motion of a high-mass object would be far more difficult than it would be for an object with only a small mass. And that concept, that feeling, that appreciation of the mass of an object relates to what we would call its inertial mass. Masses have inertia, a kind of difficulty in getting them to move, or in getting them to stop moving, or to change the way they move, regardless of the presence of other forces like friction and the like. Okay, coming back down to Earth, we are also all aware that on the surface of the Earth, high-mass objects are pulled strongly to the Earth by what we are used to calling the force of gravity, and low-mass objects less so. One way of looking at this is to say that from Newton's second law, F equals ma, the gravitational pull of the Earth on the object makes it accelerate towards the centre of the Earth. As we'll see later, this acceleration is the same for any value of mass at a place on the Earth's surface, and we call it the acceleration due to gravity, and we usually give it the symbol little g. Of course, if this is the acceleration for a free-falling object near the Earth's surface, we can say that the force of gravity on the object by Newton's second law, F equals ma, is simply given as F equals mg. This force F, pulling the object to the ground, can be thought of in Newtonian mechanics as the weight of the object, and clearly if m is in kilograms and g is in meters per second squared, then the weight of the object would be in newtons. This weight of an object, this force from gravity, is obviously from, amongst other things, the mass of the object, but one would be hard-pressed at this stage to say it has something to do with the inertia of the object, or its inertial mass. It seems that it's not so much to do with the inertial property of an object, but rather some kind of gravitational property. It's as though at this stage in our thinking, at least, there are two types of mass, or rather, two types of properties of matter. We might call them inertial mass and gravitational mass. And they seem to appear in our formula as the same thing, and yet they seem very different. One has to do with changing the movement of an object, and the other has to do with the gravitational attraction of the object to another mass. And this is one of the issues that many people struggle with. And by that I mean those people who study Newton's equations of motion and of gravitation, and who think a bit more deeply about them. This is something which will be explored in future discussions, and when, at a much later stage, we eventually get to general relativity, we'll see how Einstein's theory helps to clarify this connection. Okay, having looked at some basic Newtonian mechanics, essentially Newton's second law, we want now to give a brief overview of Newtonian gravitation, simply as a reminder and to bring out a few points. This theory from 1687 has been tremendously successful in describing and predicting a large number of mechanical processes. For example, for the moon landing of Apollo 11 in 1969, the journey of 4 days, 6 hours and 45 minutes to the moon was predicted with incredible accuracy by Newton's laws of gravitation and his laws of motion. Nevertheless, the theory had a number of issues with it. Not least was the fact that there were small but measurable errors in calculating the orbital motion of the closest planet to the Sun, Mercury. The way in which Mercury's elliptical orbit kept precessing could not be completely explained by Newtonian gravitation, there seemed to be something fishy going on. And on top of that, there were a number of more philosophical issues, which will probably be familiar to those who have ever tried to teach Newtonian gravity. These will be mentioned as we go along, and this brief discussion will also serve to define a number of important variables and relationships which will be needed and will be good preparation for the later discussion of general relativity, or what we might call Einsteinian gravitation. That theory will not only explain the orbit of Mercury, but will also help to overcome some of the other more tenuous issues. We start then with the basic idea that two masses will attract one another by virtue of their mass. Consider two spherical masses m1 and m2, whose centres of masses are a distance r apart. Note, we're using the idea of centre of mass, or even loosely centre of gravity here, for simplicity, in order to avoid having to consider some Gaussian ideas at this stage. We'll need to get into the simpler aspects of Gauss's theorem in later videos, but for now, we'll think in terms of each object having a centre of mass, where when studied from the outside, all the mass seems to reside. The magnitude of the force of attraction between these two objects is found to be proportional to the product of their masses and inversely proportional to the square of the distance apart, the distance between their centres of mass. F is proportional to m1 m2 over r squared. Once again we have a proportional sign, but this time we can't arrange for it to be equal to 1 because all the units in the equation have already been defined. Instead, the constant of proportionality has to be measured by experiment, and it's written in as capital G. It is known as Newton's constant of gravitation, or the universal gravitational constant. We have therefore for the magnitude of the attraction of these two masses, F equals g m1 m2 over r squared. This constant g is actually quite difficult to measure with any great accuracy. It's now known to four significant figures to be 6.674 times 10 to the minus 11 meter cubed per kilogram per second squared. It not only appears here in Newton's gravitational law, but it will also be seen in the Einstein field equations of general relativity, which come much later in this series of videos. In those equations of Einstein, the gravitational constant big G will multiply the term containing the stress energy tensor T mu nu, which is sometimes called the energy momentum tensor, and it will be an important factor in relating that tensor to the geometry of space-time. But that's for later, if you were to stick with this series of videos, much later. It should, I suppose, be obvious that here, each of the two masses attracts the other mass with the same magnitude of force, though the directions are opposite, and we know this is an example of Newton's third law, which can be stated to every action there's an equal and opposite reaction. And this obviously means that the force on m2 by m1 is exactly equal and opposite to the force on m1 by m2. Now you may wonder why the Newtonian formula here has been written as a magnitude formula, whereas it should really be a vector formula, and there's a reason for that, and we'll discuss that a little later. Regardless of that, if m1 is the Earth and m2 is a small object on the Earth, then the same law applies. We'll put the mass of the Earth as capital M and the mass of the much smaller object on the Earth as little m, and we'll also give the supposedly spherical and homogeneous Earth a radius of capital R. We then have that the magnitude of the force of attraction between the Earth and the small mass on the Earth is F equals gmm over r squared, where on account of the very large Earth and the very small mass little m, we've taken the separation of the masses to be effectively capital R. Remember here in Newtonian gravitation, this F represents the magnitude of the force on the little mass by the Earth, pulling it downwards, and is also the magnitude of the force by the little mass pulling on the Earth, pulling the Earth upwards. If we now focus on the small mass, Then from what we said earlier, we can say that the magnitude of the force of gravity on a mass m on the Earth's surface is given by F equals mg, where g is known as the acceleration of gravity at the Earth's surface, also known as the gravitational field strength on the surface. The value of g, as you probably know, is close to 10 meters per second squared, or 10 newtons per kilogram. So, comparing these two equations, it's clear that the size of this g on the surface of the Earth is given in Newtonian gravitation by this expression, where big M is the mass of the Earth, big R is the radius of the Earth, and big G is the universal gravitational constant. Furthermore, it should be obvious that we can interpret the magnitude of this little g as the force of gravity on a 1 kilogram mass placed on the Earth's surface. It's this formula with little m equal to 1, and for that reason we can also think of this little g as the gravitational field strength at the surface of the Earth. It is the force that would act on a unit mass on the surface. Now, although we've not considered the vector nature of these forces, this little g, this force per unit mass, Newton per kilogram, is actually a vector pointing towards the centre of the Earth. If we were to go to some height above the Earth's surface, then this field strength would decrease, and it would do so as the square of the distance from the centre of the Earth. As a function of little r, the relationship is obviously gm over r squared. This expression gives the magnitude of the gravitational field strength outside the Earth as a function of little r from the centre of the Earth, and if plotted out, the relationship will look something like this. Notice here that we've not shown how g changes inside the Earth, although it's actually not a difficult exercise if you assume a uniform density for the Earth. It would be linear. The correct way to prove this straight line relationship inside the Earth is via Gauss's theorem, but you can understand its result in the following simple way. Imagine the Earth had a uniform density of ρ, and you are at the bottom of a deep hole like this. You are here at the red dot. It's very easy to show that the acceleration of gravity that you would experience at that place would be as though you were standing on a smaller Earth of the same density ρ, like this, basically standing on the darker blue sphere shown. The outer light blue shell, which would be above and below you, would produce zero resultant force on you. If you like, although this part of the ring has quite a lot of mass near to you and will attract you with the resultant force upwards in this diagram, there's a whole lot more of the ring, granted further away from you, that will produce a resultant force downwards on you. Being more of it and further away, this lower part of the ring will produce a downward force which turns out to be equal and opposite to the upward force, and hence they balance one another out. The resultant force on you from this whole ring will therefore be zero. The acceleration of gravity that you will experience will be as though you're standing on this smaller version of the Earth, which will be pulling you to its centre of mass. This means that the 1 over r squared gravitational law, coupled with the 4/3 pi r cubed mass density relationship, combine together to show that the acceleration of gravity will decrease linearly. R cubed over r squared is r, once you're inside this uniform density Earth. Of course, if, instead of the Earth, we were dealing with a point mass, capital M, of zero size, a singularity with the mass of the Earth, then the relationship for little g against r would look like this, as the size of the acceleration of gravity or field strength increased towards extremely large values. So, given this important relationship between the strength of a gravitational field little g and distance from the mass capital M which produces it, we could picture the gravitational field using radial lines pointing towards the centre of mass. This illustrates how the gravitational field around a mass such as the Earth would pull other masses towards it, according to this Newtonian explanation of gravity. At this point, for example, at some radius little r from the mass, the formula for g of r would tell us the force that would act on a 1 kilogram mass placed at that point. And that would mean that if a mass little m were to be placed at that point, it would have a force on it towards the Earth of m times this value. In other words, m little g. And if we were to consider the vector nature of all this, we would probably make the force and the acceleration here both negative, because they're each pointing towards the Earth, and so they are in the opposite direction to the outward radius vector r. But I think you can see that the basic physics is fairly straightforward. The field strength on the Earth's surface, or what we usually call the acceleration due to gravity at the surface of the Earth, will be given by substituting the radius of the Earth, capital R, into the formula. And at some height h above the Earth, it will be less than this, namely given by this expression. This weakening of the gravitational field as you get further away, which is obvious from the formula, is also seen in the fact that the field lines get further apart at greater heights. The gravitational field is weaker here than here, indicated by the lines being further apart. We'll talk more about this later, but you are, I'm sure, already aware that in any kind of field, if the lines get further apart from one another, the field gets weaker. Conversely, of course, if the lines get closer together, near the Earth, the gravitational field becomes stronger. The other thing to notice here is that not only does the field get weaker as you get further away, it is strictly speaking non-uniform everywhere. The field lines here are never parallel and equally spaced, which is what they would need to be for the field to be perfectly uniform. The gravitational field lines are always converging towards the centre of mass of the object which produces them, in this case the Earth. We can never therefore have a truly uniform gravitational field with nice, parallel, equally spaced field lines when we're dealing with masses. On the other hand, I suppose, if we zoom in to a small region, say near the Earth's surface, the field lines will be close to being parallel, and we may even approximate them as all being vertical to the Earth's seemingly flat horizontal surface. This, of course, is a good approximation for calculations near the surface of the Earth. Over small areas of the Earth's surface, the Earth is essentially flat, but also the acceleration of gravity can be taken to be constant and directed vertically downwards at the surface. Even up to reasonably small heights above the Earth, the acceleration of gravity g can be assumed to have the same value as that on the surface, and the field lines can be taken as being parallel. And this allows us to do various calculations in relation to moving objects near the Earth with quite good accuracy. However, we should never forget that this idea of a uniform gravitational field is an approximation, and the gravitational field lines due to the Earth, or due to any mass, are strictly speaking non-uniform everywhere, even on the surface of the Earth, where they only approximate to being parallel. As you'll see later, this whole issue of non-uniform or never uniform field lines around masses will become important when we begin to think about general relativity. Another concept that can be confusing when studying Newtonian gravitation is the notion of weightlessness. The idea of weight was introduced earlier, and it was said that, using the ideas of Newtonian gravity, weight is often defined as the force of gravity on an object. Using this definition, we would say that on the Earth's surface, the weight of a mass m is given by mg. This definition of weight fits in with the ideas of Newtonian gravity in the sense that an object with a given mass would have a different weight on different sized planets or on the moon, and yet the mass would be constant. Consequently, the weight of an object of mass little m on the moon, mg moon, will be less than its weight on Earth, mg Earth. Furthermore, when the mass little m is in deep, deep space, far away, let's say infinitely far away from the gravitational pull of any other objects, we can say that any gravitational forces on it are effectively zero, and that means that the gravitational field strength g in that region will be zero. And if we were then to ask what the weight of the object is, then, according to our Newtonian definition of weight, it would have to have a weight of 0. The mass at infinity could be said to be truly weightless. By this Newtonian way of thinking, it will float in space with no forces on it. It has, by this definition of weight, no weight. And this all makes sense. However, where students of Newtonian gravity can get confused, and where these ideas don't seem fully to make sense, is when students come to consider things like objects in orbit around, say, a planet such as the Earth. Suppose a spaceship is in Earth orbit, some height above the Earth at radius r from its centre, going round and round in a stable, circular orbit. The occupants of the spaceship will be floating around inside the spaceship and will be considered to be weightless. However, they are still relatively close to the planet Earth, and they still, according to Newtonian gravitation, have the force of gravity on them pulling them to the Earth. Indeed, it's this force of gravity which keeps them in orbit. The Newtonian equation of motions are clear as to how this force of gravity on them produces circular motion with orbital velocity v or angular velocity omega. The gravitational force of attraction to the Earth must have a value equal to that required for circular motion, mv squared over r or m omega squared r. So, in thinking about the floating objects of an orbiting spaceship, the question arises, if we define weight as being the force of gravity on an object, how can we say that the astronauts are weightless in such a situation? They have the force of gravity on them, so surely they have weight. Surely they're not weightless, at least not by that definition. Now granted, we can understand and explain this phenomenon of floating in an orbital spaceship by saying that the spaceship and things inside it are falling together, and so the occupants float within the spaceship. But one can appreciate the confusion that this definition of weight can produce in the minds of some students. We say the astronauts are weightless, and yet they still have the force of gravity on them, which is how weight has been defined. Indeed, the astronauts must have the force of gravity on them to keep them in orbit. And this inconsistency and difficulty in the language of Newtonian gravitation is one of the things that general relativity will be helpful in sorting out. It won't deal with forces in the same way. An important being that anything in free fall will be considered not to be accelerating, and anything held at rest near a large mass will be considered to be accelerating, which at this stage probably seems like nonsense. For example, the guy here who is standing at rest will be said to be accelerating, due to the ground pushing him upwards. No mention of any force of gravity in general relativity. On the other hand, the guy in mid-air falling out of the tree is said not to be accelerating, but to be in free fall and travelling at some constant velocity along a geodetic. Again, there's no mention of any force of gravity in general relativity. However, general relativity, when we get to it, although containing what might at this stage seem like very strange ideas and formulae, will allow us to calculate what in Newtonian gravitation we call the force on the guy who is standing here and at rest. General relativity will give us a formula which, if we set the velocity of light to be infinite, will end up giving us the Newtonian value for the force on the person, what we might call, in Newtonian gravitation, his weight. But that's for later, if you want to think about general relativity. Much later. Newton's equations of motion and his laws of gravitation here are fairly simple and straightforward, and yet, as we've said, they throw up a few surprising and even confusing issues, including the weight issue. Here's a list of a few of those issues that I believe it has thrown up so far in this little discussion. Number one, there seems to be two types of mass, inertial mass and gravitational mass, or at least mass has two very distinct properties, one to do with the difficulty of changing its motion, and one to do with how it attracts other masses, and yet we treat it as the same thing, mass. Secondly, gravitational fields are never really uniform fields. They're always converging near large masses and maybe diverging in parts of complex systems, but they're never truly uniform over extended space. And thirdly, the definition of weight and weightlessness in Newtonian gravitation seem somewhat confusing, both in the definition of weight and in the language used, for example, when we talk about weightlessness. Leaving those questions hanging for the moment, we come in this next section on Newtonian gravitation to think a little about the potential energy possessed by objects in a gravitational field, that is, in the gravitational field of some other massive object. For example, clearly an object on the surface of the Earth has less gravitational potential energy than the same object which has been lifted to some height above the Earth. The reason, we would say from Newtonian mechanics, is because work would need to be done to lift the object to that height above the Earth. This small mass positioned here on the surface of the Earth has less potential energy than the same mass positioned here. And in order to quantify this, it's usual to introduce the idea of the gravitational potential at different places within a gravitational field. Every point in space will have a value of this gravitational potential, and it will be equal to the potential energy per unit mass of an object placed at that point. Gravitational potential at a point equals the potential energy per unit mass at that point. In other words, if we have a gravitational field around a mass capital M, then in SI units, the gravitational potential of some point in space around it will be the potential energy which a mass of 1 kilogram would have if placed at that position in the field. The SI units of gravitational potential will therefore be joules per kilogram, energy per unit mass. This point will have a gravitational potential of some number of joules per kilogram, and this point would have a higher value of gravitational potential. Higher because a 1 kilogram mass placed here would have more potential energy than one placed here. Work would have to be done against what we call the force of gravity to move the 1 kilogram from here to here. And that's fine, and we could probably calculate the differences between different places using the formula we've already got. But an important question is this: where should the zero of gravitational potential be? At what point in space should we take the gravitational potential of an object to be zero? Once we've got that, we can calculate information about every point in space from it. But where should we make the zero? Well, if you take time to think about it, the logical place for the zero of gravitational potential is infinity, an isolated infinity. In other words, that place where the gravitational effects of all other masses in the universe are zero or negligible, a place where a mass would be totally isolated. Using that place as our zero of gravitational potential, the calculation of the gravitational potential at any point near a massive object M is fairly trivial, and it goes as follows. Consider a mass capital M. It could be a point mass or an extended massive object as shown here, around which we would like to know the gravitational potential and how it varies with position, or rather radial distance, r. Consider also a small mass little m at some distance little r away from the first mass. If we calculate the work done to bring little m from infinity to that point, then assuming it had zero energy at infinity, then the answer to that work done, or force times distance, would be the potential energy of little m at the distance r. If we then divide this answer by little m, we would then have the gravitational potential at the point r. In other words, the energy required to bring a unit mass from infinity to that point. We would need to integrate, of course, to get the work done, because the force of attraction is changing as the mass moves from infinity to r. I'm sure you also realise that this potential will come out as a negative answer, because positive work would need to be done to move the little m outwards towards zero at infinity. That means that in coming inwards, the work done must be negative. Anyway, the integration to find the work done in bringing little m from infinity to r looks something like this, where you'll see I've not been rigorous about the vector nature of things, for reasons which will be given later. And if you work through this, you may want to think about the directions of the force and how the negative sign comes about. The work done is the integral from infinity to r of force times distance. This answer to the integration, minus gm over r, is the potential energy of the mass little m at a position r from the mass capital M. So in order to find the gravitational potential at that point r, we simply need to divide by little m, and this then gives the gravitational potential around a mass capital M as minus gm over r. It's negative, as expected, and it is an inverse linear relationship, 1 over r, as opposed to the inverse square relationship we have for the gravitational field, but it does drop off to 0 as r approaches infinity. This gravitational potential is a scalar. It has a value, but in no sense can it be said to have a direction. In SI units, it would be measured in joules per kilogram, and we will give it the symbol phi, which is often used in physics for scalar fields. You may see it sometimes written as capital U, but we will stick to phi. We can then say that the gravitational potential at a distance r from mass capital M is given by phi equals minus gm over r. A plot of the relationship between phi of r and the distance little r from the mass capital M, which has a radius of capital R such as the Earth, will look like this, with a minus 1 over r relationship. Again, in this diagram we've not considered the gravitational potential inside the mass, although once more it's not difficult to calculate that for a uniform or homogeneous object. It would have a quadratic shape towards some finite value at the object's centre. And if you think about it, that happens because the 1 over r gravitational potential relationship, coupled with the 4/3 pi r cubed mass density relationship for a large mass, which could be the Earth, combine together to leave us with the gravitational potential decreasing according to r squared once inside the uniform density Earth of mass capital M. Also, of course, if the mass under consideration capital M was a point mass, a singularity, or just very small, the curve would continue to go on as minus 1 over r towards the mass, something like this. This scalar field, as we might call it, of the gravitational potential fills the space around the mass capital M. Every point in space will have a value of this gravitational potential, but remember there's no direction involved. It's just a value. We could imagine contours of constant gravitational potential around the mass, and these would be concentric spheres, which we show here as circles. They are equipotential surfaces, and we can imagine adding spherical surfaces out to infinity, and their potential values would tend to 0 there. You should realize that for equal changes in energy, these lines, or spheres of equipotential, get closer together as they approach the mass, and you may even realize that this is related to the fact that the gravitational field g of r at any point in space is equal to minus the rate of change of this potential with distance at that point. If you like, the gradient of the gravitational potential from one surface to another, from one circle to another here, gives the value of the gravitational field. It's a bit like contours on a map. These map contours are, in a sense, equal height lines, and the closer they are together, the steeper will be the gradient of the slope. And so it is with gravitational potential. The closer the equipotential surfaces are together, the more quickly the potential changes with distance. And this means that the gravitational field is stronger in that region. the gravitational field is equal to the slope of the way the energy per unit mass changes with distance, or strictly with the vector displacement. Mathematically, you can think of this differential relationship as being the opposite of the integration that we had to do in order to get from the field g of r to the potential phi of r. This differential relationship gets us back to the gravitational field g from the gravitational potential phi. You can check this out by actually doing the differentiation. The gravitational field strength g is minus the differential of the gravitational potential phi with distance, which turns out to be minus gm over r squared as expected. Now, although this whole concept of gravitational potential phi is important in thinking about Newtonian gravitation, and we will use it briefly later, when you start to think about general relativity, it will, in some ways, be redundant, because the focus will be on something called the metric tensor. But again, that will come later if you want to stick with these videos and get into some general relativity. However, we'll now think a little bit about escape velocity. Using these kind of energy considerations, it's easy to calculate the outward radial velocity that an object would need in order to escape completely from a gravitational field. In other words, to get it out to infinity. Consider an object of mass little m positioned somewhere in a gravitational field, some distance little r from a mass capital M, like this. Little r could actually be on the surface of the large mass, or some distance from it, as shown here. Wherever it is, the object little m will be at a place where the gravitational potential phi is given by minus gm over r, and we could then say that, with respect to infinity being 0, that object would have a potential energy of minus gmm over r, where we've simply multiplied by the mass little m. Now suppose we wanted the object to escape from that field completely, to where the field value is 0, to where its potential energy would be 0, and suppose we wanted the object just to escape, in other words, to have no residual kinetic energy once it escaped. In that case, it would need to start with a velocity outwards and a kinetic energy such that it could just get out to infinity. So, if moving radially outwards, the kinetic energy of the mass, half mv squared, would need to be equal to the required change in potential energy, gmm over r, and that would mean that the radially outward velocity would need to be such that its square was 2gm over r. And so the required value of that velocity would need to be the square root of 2gm over r. And this v is known as the escape velocity, and as you can see, it is independent of little m. In other words, it's the same for every object at this distance little r from a mass capital M. For example, the escape velocity of any object from the surface of the Earth is around 11.2 meters per second, or 25,000 miles per hour. Now, with an eye to thinking about general relativity later, we could make a very simplistic argument about a beam of light escaping away from a large mass to infinity. In the next video in this series, we will discuss the equivalence principle and the idea that gravity can bend light. Gravity can, in a very crude way, be said to attract a beam of light. And if that's the case, then this formula for escape velocity gives us a Newtonian hint about the criteria for a beam of light to be able just to escape from the gravitational field of a large mass capital M. Putting v in this equation equal to the speed of light gives us this, and rearranging gives us r equal to 2gm over c squared. And this r is called the Schwarzschild radius for a mass capital M. It is the radius at which a beam of light travelling radially outwards can just escape the gravitational field, and we will give it the symbol capital RS. Now, even though this idea and formula has come about from a rather simplistic use of Newtonian gravity, this value of the Schwarzschild radius will become important when we discuss general relativity and the properties of black holes. In particular, we will be thinking of a very large value of mass concentrated in an extremely small volume, something like a black hole. It's shown here with a finite but small size for convenience, the blue dot at the centre. For such a highly concentrated mass, capital M, there will exist an imaginary shell outside of it at the Schwarzschild radius Rs. This shell is called the event horizon. Any beam of light originating outside this shell, or this radius, and travelling radially outwards will escape to infinity. It will have an escape velocity, the speed of light, greater than the value required at the point where the light beam starts. And we've shown it crudely here as a flashlight. However, any beam of light originating inside this shell, even if it's travelling radially outwards, will not escape from the black hole, but to put it crudely, will be pulled back to the central mass. Its velocity, the velocity of light, will not be enough to escape from the black hole. This event horizon is a kind of boundary, and the strange things that arise from this Schwarzschild radius will be discussed in a little more detail once we've done some general relativity and we focus on what we call the Schwarzschild metric. But before we move on, however, it's probably worth mentioning one more thing about this. All masses, if they can be reduced to a small enough size, can become black holes. If, for example, you use the Schwarzschild formula and put in the mass of the Earth for capital M, the Schwarzschild radius comes out to be about 9 millimeters. That means that if the whole of the mass of the Earth could be shrunk to a good deal less than a centimetre, then it would have an event horizon at a radius of about 9 millimeters. It should be obvious to you, however, that this does not mean that if you could go down to almost the centre of the Earth, there would be a black hole there. From what we discussed earlier, it should be clear that as you get nearer to the centre of the Earth, the gravitational field gets weaker and weaker because essentially the mass involved in creating any Newtonian force of gravity on you is the mass of the sphere at that particular radius. And most of the mass of the Earth in the light blue section here is of no consequence. Okay, we had this classical discussion of escape velocity simply because we had been looking at gravitational potential following on from some seemingly confusing aspects of Newtonian gravitation. Before we move on to the next video, we should clarify one more important point. We mentioned earlier that in having this discussion on Newtonian gravitation, we have totally ignored the vector nature of many of the equations. We simply talked about the magnitude of the forces and so on. And there's a reason for this, and it often crops up when teaching topics such as this in physics. For example, we gave the equation for the magnitude of the force between two masses m1 and m2 as gm1 m2 over r squared. And that's fine for the magnitude or the size of the force. However, we tend to think of this as a vector situation. Force is a vector after all, and in this case the force is opposite to the direction in which r is measured. And a possible way to show the vector nature of this would be to write the Newtonian formula as this, where the vectors are shown in bold and not italic. This is a scalar, the magnitude of r cubed, and it has to be cubed so that we can have a vector r on the top, so that we have an inverse squared altogether. We can now sensibly have the minus sign in this equation, showing that the force F between the masses is in the opposite direction to that of r. R is measured outwards, force is acting inwards. However, although this equation puts things more accurately for this inverse square vector law, it looks horrible and can be quite confusing, especially as equations build up in complexity. And for that reason, we often use only magnitude equations such as this, or we may even cheat sometimes and put in a negative sign, even though mathematically this doesn't really make sense. On the other hand, of course, I should say, in the potential equations, the negative sign is entirely appropriate, because in that case we're dealing with a scalar which can simply have a positive or negative value. It's not a question of direction in space. And the issue of writing vector equations in a rather sloppy way will occur now and again throughout these videos, but we'll try to remember to add a reminder when it happens. Okay, this video has discussed the basics of Newtonian gravitation and has highlighted some of its deficiencies. In the next video, number 2, we will consider one more apparently strange aspect of Newtonian gravity, namely that a uniform acceleration can appear to mimic an extra force of gravity, what Einstein referred to as his happier thought. This will then allow us to introduce the equivalence principle and to see how Einstein used this and other ideas to introduce his general theory of relativity, a theory which would address the problems associated with Newtonian gravitation. This video, as a simple introduction to general relativity, has reviewed the ideas of Newton and thought about some of the inadequacies of his theory of gravitation. The next video in this series, number 2, will consider inertial and non-inertial frames and will lead to the equivalence principle. It will then discuss coordinate transformations and take a brief look at Gauss's theorem.